Bartnik data.
But that's okay.
Oh, I apologize. That's
fine. I know that there's a can be a wide variety of background in the audience. This helps can be very non-technical, and I think these are actually writing down some definitions that are writing down. So let me start with something. Oh.
It's okay. So let me start with something that I think is pretty well known, but let me just say that I'll be working with manifolds of dimension n, and they're always at least 3-dimensional. So well-known theorem due to Shane Yao, Gromov-Lawson. So I'm not going to always be stating the most detailed versions of theorems, but basically that if you take a torus and connect some anything, that this does not admit metrics with positive scalar curvature. Positive scalar curvature, or I guess maybe I'll just say PSC, so I don't have to keep writing it out. So of course this is the torus. This is a compact manifold. Okay. And actually I don't remember what year it was, but not too long ago, a few years ago, I guess. This theorem was generalized by Otis Chodosh and Chao Li. Okay, and what they showed was that if you take this, that you can't even do it even if you allow xn to be non-compact. In other words, as long as it's complete. So this does not admit complete PSC. Okay, and here the difference is that this is just any manifold now. Okay, without boundary. Okay. And so the tool that was used was mu bubbles. Okay, so we heard a little bit about mu bubbles, and so maybe this will be the only thing in the talk where I'll actually bother to really write out what it is, even though I'm not really going to say much about using mu bubbles necessarily, but I do want to say why mu bubbles here are handy. So I think what's already mentioned that Gromov really promoted the use of mu bubbles in scalar curvature questions, and that has we've seen it to be fruitful. And so here's a definition. Actually, definition may be specific to the context that I'm interested in for this talk. So given a Riemannian manifold Mg, and we're going to have a function h into the extended reals, and I'm going to have an assumption. I guess I'll take. Maybe I'll just draw a picture that okay, so maybe I'll say M0 is the set where H is finite and the closure of that. Okay, so the picture I want to have is something like, here's M0, and then out here H is maybe minus infinity, out here is plus infinity, and then so the boundary of M, let's say, has two components, say the plus side and the minus side. Okay, and this is all just an assumption. I'm assuming that I have this setup, and yes. Yeah. Sorry about that. It's written in my notes, but I'm kind of just going off memory. So yeah, thank you. 10 less than or equal to 7.
Was that Sam?
That would be funny. Okay, no. Yeah. less than or equal. Okay, thank you.
Thank you.
Yes.
7. 7 goes.
7, yeah, n is less than or equal to 7. Thank you. Thank you for pointing that out. Okay, so so then what I'm going to do is consider omega with maybe. Yeah, I mean, there's an argument for general dimension. It's out there. So consider omega contained in M, and such that let's say the boundary is contained in the is contained in the M naught part, I suppose. Or actually, maybe I should just say that yeah, I'll say the boundary is contained in the M naught part, and that omega contains, say, the plus part. So the picture you should have is that omega is like this, right? So it's just something. So in the context that I'm interested in, I guess usually M naught will be compact. Okay. So the reason why is that way I can talk about volumes and areas and they'll be finite. So we have this functional, which I think, again, Professor Shi already mentioned, sometimes called a brane functional if you're a physicist. But this will just be the, I guess, the n-1 Hausdorff measure of the boundary of omega. And then I subtract off the weighted volume of omega, but I only want the finite part. So I'll just do omega intersect M naught. And then I integrate H over that. So H is a weight for computing volume. So it's a weighted volume. So it's the area minus the weighted volume. And of course, for the technical minded, right, this omega is like a Cacciopoli set. And this is actually the perimeter or the measure of the reduced boundary or whatever, all that stuff. Okay, so that's the functional, right? And then critical points are called mu bubbles. Or somewhat, mildly abusively, the boundary of the critical, the critical point is actually omega, but we usually call the boundary the mu bubble, or sometimes we call omega, I don't know what we call it, but so those are called mu bubbles. And again, maybe I've gone too low on this board, so let me go over here. Okay, and then the important fact again, which has already been mentioned, is that the mu bubble, right? Has the mean curvature is exactly equal to H. So the critical points have the useful feature that we have the exact specified mean curvature, at least, but where H is a function, right, on the manifold. Okay, and again, so for n less than or equal to 7. So one reason why I set it up this way rather than full generality is that this is a situation where you can always construct the mu bubble. So for n less than or equal to 7, mu bubble exists and is smooth. And this is in the paper by Jintian Zhu. But let me just mention conceptually, right, how this works. So if you're familiar with minimal surfaces or minimal hypersurfaces, you'll know that if you had a boundary with, signed mean curvature on one boundary and signed mean curvature on the other boundary, opposite signs, and I won't say which signs because, that's something you work out at home, but that implies that there has to be a minimal surface in between, So this is a generalization of that same idea. And it works really nicely here if you just take H go to plus infinity, because it's just like, well, that really forces the a barrier to be there. Okay. All right. Well, yeah. So sorry. So maybe say under this assumption, namely the one that I have on the board on the left. Okay. So So obviously these generalize minimal hypersurfaces. Sorry, I should say CMC, yes. So under this assumption, I don't just want mu bubbles. I actually want stable mu bubbles exist. Okay. So I can always get a stable mu bubble. All right. And well, you know, it can't just be everything for free. There's a cost here. I had to put this h in, and that's going to affect the equations. Okay. So yeah, it's smooth in M0, but I guess, you know, it goes to plus minus infinity. So it's smooth in the interior of M0, and then it hits infinity at these two boundaries. And, you know, usually I'll choose it so actually so these, maybe those are smooth even to make things like simple, I suppose. But yeah. Okay, so so there's a fundamental observation of Shane and Yao, which is that if, and I'll just again state it fairly simply, if you know that the scalar curvature of your ambient manifold is positive, then that implies that stable minimal hypersurfaces admit PSC, let's say. Okay, so this isn't a compact, just for simple, this is a compact setting. Okay, basically, it's if you look at the stability inequality, right, then you can see and compare that to conformal changes, then you can see you can conformally change it to have PSC. Yes.
About the existence of these new bubbles, maybe there's some min-max methods, maybe could be by the scaling of that function over there. It seems that the h is constant, and I pick larger and larger sets. So in that sense, the penalty coming from a constant positive, the penalty coming from the volume wins. So in that sense, there are no minimizers.
Yes, what you're saying makes sense.
Greater to the n. So if I want to minimize, I just pick all of the greatest n.
Since h is not constant, so he's making the assumption that h is not constant. In fact, if you dilate too much, if it gets too large,
so that's the point. So still are minima. So critical points are found as minimum of the function.
So they're not just stable; they're actually minimizing.
So that's
yes.
Okay. Okay.
Yes.
At least locally.
What was go just on this side where h is
Yeah. Okay. Oh well. Okay. Sorry. I may have misspoken here because okay. So all right. So technically, so let me just. So I actually integrate over omega. Oops. And then I subtract some reference amount so that these are the integrals are finite, let's say. Sorry, so so this number could just be infinite just because like the h is big, right? So like I'm saying, well, you should actually subtract off like just like a fixed reference amount because you're only interested in the differences between things, not actually. Oh no, it's a multiplication. It's, I mean, that's. Oh, it's chi. Those are no indicator functions. I'm sorry, indicator functions. Thank you. Sorry. Yeah, these are chi's, not x's. Okay. Sorry. So does that help a little bit? I should have been more careful with that.
Why do you call them mu bubbles and not h bubbles?
That's a very good question, and I'm not responsible for that. So I think originally they were mu bubbles, and then people started using it, and they started calling their function h instead of mu for some reason. And so I'm just following what the other people in literature have been doing. Don't blame me. I agree it's silly, but yeah. So So originally there were mu bubbles. The weight was mu, I guess, but I don't know. Yeah. So so here the observation is that if you have, bringing the H into it, of course, puts new factors into the stability inequality. So instead, what you get is this again, which this was already described in Professor Xi's talk. But instead, you get, if you have this inequality, then stable mu bubbles admit PSC. Okay. So the game is, if you want to get some kind of usefulness out of this, then you need to like design H so that that this inequality holds. Okay, and that's the fundamental idea behind the Chodo-Schlee proof. I mean, it's not. I should just be careful. It's not just taking the Schoen argument and changing. There's actually some cleverness to it, where they had to construct some stuff. But fundamentally, it's about finding an H that does what you want it to do. Okay, so that's the background. Here on mu-bubbles. I guess I'm going real slow. Let's see. Okay. So let me just say this has already been stated also. So maybe I'll do it even faster. But so the positive mass theorem. Yeah, it's just Gromov-Lawson uses a spin method, so it works for spin manifolds. Similar deal here. Witten's uses spin, so it applies to spin manifolds. But so if Ng is complete, asymptotically flat, which sometimes I guess I'll abbreviate AF so I don't have to keep writing it. If it's complete, asymptotically flat, and non-negative scalar curvature, then ADM mass of each end is non-negative, greater than or equal to 0. Okay. There's also rigidity, but let me save time by not writing it down. Okay. So in a similar spirit to this result, you can actually replace the other ends. The asymptotically flat ends can be replaced by arbitrary complete ends. Okay, so here's the theorem. So I guess I'll call PMT arbitrary ends. I mean, arbitrary complete ends, I guess, is the right way to say it. So so this theorem is says so n less or equal to 7. Actually, this is also true for spin manifolds, but let me just say n less or equal to 7. It says, so if Mg is complete and has a asymptotically flat end, again, I would need non-negative scalar curvature, then the mass of the end is 0. So it's greater than or equal to 0. In other words, here is basically, it's not written explicitly, but it means every end is an asymptotically flat end. That's the original theorem. Here it's just saying, well, if you just have one asymptotically flat end, the other ends can be arbitrary complete ends, and you still have this. So it's kind of in the same spirit as the Chodo-Schlee. And so let me just say this is due to, so the first, I guess, is a Bartnik Kruskal. This is for spin manifolds, but so let me just say or spin since I'm writing it now. Spin manifolds also see Cecchini and Zeidler, who also do a spin proof, but it's actually kind of a different spin proof. So that's for spin for n less than or equal to 7. Well, I guess this is combination of, I guess, or Lesueur, Unger, Yao, and Jintian Zhu, and the paper I wrote with Lesueur and Unger. And let me describe a little bit about how the argument breaks down. Not breaks down, I mean, what the pieces of the argument are. So let me just say that for the proof of the Shane-Yao positive mass version of the positive mass theorem, it has essentially two main parts. So there's the famous part and the not famous part. So the famous part is prove it for asymptotically short shield. So this is the most important case, obviously. I think so. Just to let you know what this means, since it's been mentioned today already. So asymptotically flat, which I haven't written down, but it's saying that the difference between the metric and the Euclidean metric has some kind of decay, and asymptotically short shield just means that the top order of that difference is basically the top order term is the short shield term, and then the rest of it can be different. Okay. So the first step being prove it for asymptotically short shield. This uses minimal hypersurfaces. Okay, and I don't want to get into the proof, obviously, but let me just say quickly why this matters. And the reason is because they assume that the mass is less than 0, and they use that to give you that these sort of large coordinate planes have good sign on the mean curvature, which allows you to do what I said before about barriers for creating some minimal hypersurface in between. So that you cannot get started with that unless you have like the combination of negative mass and asymptotically short shield, because that asymptotically short shield is telling you some nice stuff about infinity that you can't get just from the general asymptotic flatness. Okay, and then this then gets to contradiction to the PMT of one dimension below, but it's not the important part that I want to emphasize. So, and then the second part is you use a density theorem to reduce to that case. Right. So this is that's the non-famous part. Okay, but I find it very interesting. It doesn't use minimal surfaces at all. Okay, so with that said, I can now break down the proof of this one a little bit. So I'll call this theorem A. So let me just say the proof of theorem A. Well, that first step was just like replace. It's more complicated, I guess, a little, but I'll say more about it a little maybe later. Replace with new bubbles, and this is this was what they did in Lesueur, Unger, Yao. And then so the second part is well, you could do a density theorem. Okay, it's not the same density because there's this annoying thing where you have these other ends that are complete, and you don't want to assume anything else about them other than that they're complete. And so that doesn't really give you a lot of control, but you can get around it. So actually, well, okay, I won't get into that, but this is so this was independently done by Zhu and by us. So I'll say Li, okay, all you. Okay, so so that's the first main thing I wanted to mention. Let me just say also that this theorem, it's not just generalizing for generalizing's sake. Like there's some reasons to care about this. So the original motivation, which actually predates this even, or this theorem I should say, is that they wanted to prove this Shane-Yao-Liouville theorem, which needed this sort of statement. And these sorts of objects also come up naturally if you're solving the Jang equation, because you get ends that are asymptotically cylindrical instead of asymptotically flat. They're also, I guess, physical because they show up in, like, I guess, extreme Reisner-Nordstrom, I think, has an asymptotically cylindrical end. So it's not like they're just totally, you know, oh, well, we can do it for complete. But so there's some reason to care. That's right. Yeah, more or less. Maybe I'll be able to say something about that. But yeah, the H allows you to control where things go. And actually, I'm going to give a theorem that's a little more complicated, but I think actually explains the idea better. So there's something else that came out of this argument, and that's this idea of, which I guess we've now come to call scalar curvature shields, just for want of a better term. So let me write down definition. So MG contains a scalar curvature shield if the following. I have, so the shield should be thought of as a sequence of 3 nested open sets, such that, you know, you can get the closure of each one sitting. What the heck? 0, 1, and 2. Why am I doing 1, 2, 3? 0, 1, 2. Okay, so 0 contains the closure of this one, and U1 contains the closure of 2. And I want to say that the closure of this in M is complete. This is basically that nothing weird happens in U0. So when I say complete, I mean complete as a metric space. Okay, so the main thing is I don't want to assume that M is complete. Just that, so everything interesting is going to be happening in U0. So I'm going to write down this somewhat long definition, but then hopefully I'll try to explain it a little bit. So I want non-negative scalar curvature, let's just say in U0, so in the big set, and I want a lower bound on scalar curvature, it's called kappa. So a strictly positive lower bound kappa in U1 minus U2. Okay, and then, okay, this one's optional, but I'm going to write it for now, and I'll come back to it. So this is that if you take the mean curvature of U0, the big set, that this, I'm going to bound it above by, say, eta. And this eta, I guess, is also a positive number. The normal is going to be pointing toward U0, but I'll draw a picture in a second. And then the last one is something that relates these numbers. And so I'll pull this down in a sec. So it says that D0, which I'll describe for you in a moment, is greater than 4 over kappa D1 minus 2 over eta. And so what is D0 and D1? They're very simple. They just represent the distances between the boundary of U0 and U1. And D1 is the distance between the boundary of U1 and U2. Okay, so let me draw the picture out here. Okay, so U2, I guess, will be everything out here. Okay, and then U1 will be everything out here, and then U0 will be. Okay, there shouldn't be another end here because it's just going off to wherever. Okay, so it's U2 is out here, U1 is all this, U0 is all this. So you can just see what is D0 is just this distance, and D1 is just this distance, whatever the smallest distances are there. And the requirement the main requirement I'm asking is, well, I need non-negative scalar curvature everywhere, that's fine, but I really want a positive lower bound out in this region, which represents U1 minus U2. Okay, so this is why it's called a shield, because this section is like the shield. Okay, so now let me try to break down some of these things to make them slightly less mysterious. So first of all, let me just say that this isn't, as I said, this is optional because you could just take eta to be arbitrarily large or infinity, okay? So if you ignore 3 and then put your hand over this, it becomes a lot simpler, I guess. So it's really just saying D naught is bigger than 4 over kappa D1. So the point is, I don't make any assumptions about M here. So this whole picture, so here, I don't care what's happening. M could fail to be complete. It could have holes in it or something, or it could be fail to be have positive scale, non-negative scalar curvature, just nothing. So in some sense, you could say it's a theorem about manifolds with boundary, but kind of like this way of thinking about it instead. Okay, so the shield is basically saying if you have enough positivity here, and you can go or you can go far out enough in this direction without violating anything, then you're free to just not worry about what's happening over there. So everything out here is kind of being shielded from infinity is the idea. So I haven't written the theorem yet, but yeah.
Sorry, where is your one asymptotically flat end?
Yes, it's out here. Okay. But I didn't. But the concept of shield makes sense even without an asymptotically flat end. But the point is, the manifold that we care about is over here. Yeah, because it's the part of the manifold we care about is sitting in the U2, and the part that we don't care about is out here. But yeah, so the end would be here. So maybe I should at least write down the theorem.
So in this case here, D1 can be as simple as one wants, right? Is that correct?
What's that?
Capital D1. Capital D1
Oh, yeah.
can be extremely small and you don't care, right?
As long as kappa comes.
But that D naught has to get big. Yeah.
So kappa has to be large.
Right.
Kappa,
Yeah.
So kappa didn't see D1
Yeah.
over there.
So there's no one way to write this, but I've written it in one particular way just because the equation comes out nicer. But you could view this as given a lower bound over some annular type region, it's telling you how much things have to stay nice before you have to start to worry. But you can view it other ways, like if you had D naught D1 that's telling you how big kappa needs to be, whatever. Yeah. Okay, so maybe now I'll talk about the mean curvature. So if you have that this is less than or equal to 0, okay, I should write the theorem down. Let me write the theorem down first. Maybe I'll put it over here so it's closer to the other PMTs that I wrote down. So this is a shielded PMT, let's say. And this is, this is joint work with Lessord and Unger. And, this is also actually, sorry, this is also from the Lessord, Unger, and Yao. Okay, because it's combination, I guess. It says that, well, if MG is asymptotically flat with a shield, so I'll just be real lazy and just call it a shield, with this, and let's say that this contains the end. Okay, and let me just for technical, I'm not sure this actually matters, but let's just say that this is compact. That like basically I'm just looking out something. Then I get that the mass is positive, strictly positive, which makes sense. I have some positivity here. Okay, so that's the shielding concept, and again another reason why I think the original reason why this might have been thought is kind of interesting is that one thing that people have often wondered about is when you look at the positive mass theorem, how much negativity in the scalar curvature can you allow and it still be true? Well, this is one way of answering. It's not a matter of quantity, but it's more about placement, right? That if you have like a band of positivity, then if you push stuff far enough away, then you can allow all the negative scalar curvature you want. That's fine. Okay. So basically, the proof of this, it breaks out into the same two pieces I described before, which is that Lessord, Unger, and Yao, they proved it using mu bubbles under an asymptotically short shield assumption, and then we just removed the asymptotically short shield assumption. But also we cleaned up this definition of scalar curvature shield to make it a little nicer, because it was not as there were some inefficiencies in the original paper, so that we made it so that it's a little bit cleaner. Okay, so now let me come back to so this is also important. So this is n less than or equal to 7. They're actually similar result for spin, and that's by Sacchini and Zeidler. I think morally they can do the same things. I don't know if it's exactly stated, but it's basically the same. Yes. Sure.
Outside of the not lower manifold can have whatever number n, scalar curvature, whatever.
Yeah. It can even just have whole, like basically it's really a theorem about a manifold with boundary, but it's kind of nicer, it's kind of more fun to think about it as like, oh, you could do anything out there. But right? Okay. But yeah, you can allow anything to happen. So it's really just saying that, you know, it's shielding, I guess that's the idea. Right, so let me just say a little bit about this mean curvature condition. So let me just say, if you put a 0 here, then that's was already known that implies non-negative, or positivity even of the mass, right? Because that's basically like, you know, it's like an outer trapped assumption, or it says.
What's the omega here?
Omega. It should be U0. Thank you. Thank you. Yeah, it's this. Okay. Right. So if you have a 0 there, then we already know that the mass is non-negative just with non-negative scalar curvature. Don't need any of this other stuff. But so this is saying that, well, you can allow a boundary with some positivity, and this is actually just like in Peng's talk. He had a positive mass theorem where you allow just like upper bound on H. But so this, you can allow this if you also play it off against some kind of shield. Okay. So in other words, you don't, or another way of saying is you don't need this inequality. You can have some give here if you know something about the boundary.
So when you look at the stuff, you're talking about 2H squared.
I'm now forgetting exactly what the upper bound he had for it was, so I don't want to. I don't want to say. Well, no, it was something about something happening away from the boundary, I think, but I don't want to get into that because I could say the completely wrong thing because it's not my research. But I think it was saying something H is less than or equal to something that was like something happening away from the boundary. That then if you have that, then it works. But maybe it was something at the boundary too, but because there were some different versions also.
Yeah, he had the other 0 components.
Yeah, he had a few versions. Okay, so that's the theorem. This is right. Okay, so let me say a tiny bit about the proof. So I knew there was a reason why I brought this up. So why is it already sort of understood with the 0 here? Because if you go back to this picture I drew over there, right? H less than or equal to 0, that's again the right sign for barriers. So that when you do that part of the argument, you don't have to see anything past that boundary anyway. Okay, so that is the fundamental idea being used here for the mu bubbles, that if we design H appropriately, right, then we can make it so that out here, our mu bubble will never even enter this zone over here. Okay, so it's like that argument, and then just like how if you have H less than or equal to 0, it means the minimal surface can't enter that zone. The shield allows me to design an H such that the mu bubble will not enter that zone. That's essentially the argument that's in the Sword-Unger Yao. Okay. And maybe I'll just say very briefly that why this also actually implies the complete version, because basically what you do if it's complete is you can create a tiny shield, so just a little bit of positivity, at the expense of changing the mass, but only by an epsilon. But then once you've created that little shield, because if you're complete, then it just goes on forever, right? So the D naught goes to infinity. So this part will always work if it's just complete. So basically, shield of any size plus complete, obviously the inequality is just true. Okay. So anyhow.
Shield is being used to construct a barrier?
Yeah, well, it's used to construct the H that has a barrier. Yeah, exactly. Okay, all right. All right, so let's go back to over here. So that's maybe part one of the talk. I don't know how much time I actually have. When should I stop?
No, you can go about 5 after because we started 5 minutes late. You have 10 minutes. 9 minutes.
Okay, so let me just say the philosophy now is that, so based on this family of results, there's this philosophy that, well, you know, complete, so this is a very vague statement I'm going to say, or shielded, you know, is kind of, it's just as good as compact for scalar curvature problems, or non-negative scalar curvature problems, I'll say, or non-negative scalar curvature, because these are the results that I'm talking about. So here's one thing about, I guess I erased the theorems that I'm trying to emulate here. But so one example is that we did was, well, you can do basically a shielded version of Chotoshley. And so what do I mean by that? Well, let's say n is less than or equal to 7, and let's say mg contains a subset, let's call it, okay, well, I'll call it m naught, but it has nothing to do with m naught, I said before. So this m naught, which is diffeomorphic to the torus minus a ball, minus an open ball. Okay? And let's say mg naught has a positive scalar curvature. Okay, then what I'm saying is that mg cannot have a shield U0 containing U1, containing U2 that contains this M0. Again, I don't want to, U0 minus M0, let's say, is compact, so there's no funny business. But in other words, you have this torus bit. You know that I have positive scalar curvature. I'm saying you cannot create a shield out here. It's not possible. Okay? So so you could, that's what I mean by, if you reinterpret Chotoshley, which unfortunately I've erased, it's saying, okay, you have this torus part. It's saying you cannot extend to make a complete manifold of non-negative scalar curvature, but similarly, you also cannot like build a shield. Okay, the proof is basically, well, okay, the H that's used in Chotoshley and the H that's used in Lestord-Ungar-Yau are on the surface very different, but if you sort of, once you understand how the proofs work, you realize, oh, it's not hard to combine them into one synthesis that will work for both things simultaneously. But so again, this has nothing to do with mass though, right? This is just about, it's just about non-negative scalar curvature. Okay, so following on that philosophy, let's talk about the fill-in problem. Okay, so the fill-in problem is, this is what the talk was ostensibly about. So given this data, let's say an n-1 dimensional closed surface with a metric and a function. So this is a metric. This is just a function. Smooth one, I guess. Okay. Well, actually, let's make this a definition first. We say that omega of one dimension higher, G, is a fill-in if basically I can identify the boundary with sigma in such a way that when you take G restricted to it, you actually induces the gamma, okay? And that if you look at the mean curvature of that boundary that's equal to eta. In other words, can you fill it in such a way that it's the metric matches and that the mean curvature matches this number here? Okay, so this is called Bartnik data sometimes. Okay, so I'll draw a simple picture. I guess here's my sigma, and then I need to fill it with some omega over here, but I do it with a metric that matches, that induces that metric, and also has the right h. Okay, the h matches. So that's what I'll call a fill-in. So the reason for so this is a natural part, and this condition, as many of you probably know, is just is designed to be tailored to the nature of scalar curvature. Okay, the scalar curvature plays nicely with matching of mean curvatures on the boundary. Okay, so natural question is, what can we say about non-negative scalar curvature fill-ins of given Bartnik data? Okay. So, I mean, there are two questions. Can you fill it? And if you can fill it, what restrictions do you have? Well, if you have restrictions on what you can have, that's also like a non-existence result for being able to fill it. So that's what I want to focus on now, is what properties does it have? And in turn, that implies like a non-existence result. So, fortunately, okay, I'll skip the easy illustrative part of the talk. Skip the easy illustrative part of talk and just go to the theorem part of the talk. So that's probably all I have left, time I have left. So really important, great theorem in this direction, though maybe not always stated as such, but this is what it is. So this is by Yu Guangxi and Wen-Fai Tam. And I'll say given, so maybe this is a slightly weird description of it, but given this, assume it isometrically embeds into Euclidean Rn as a strictly convex, well, I'll just say as strictly convex, okay? Because I know it's a hypersurface already. And let's say that eta is greater than 0, okay? Then this combination has an NSC fill-in. Sigma's, yeah, it's closed surface, closed hypersurface, thank you. Yeah, just like in the picture, I guess. But, okay, so it's an NSC, has an NSC fill-in. That implies that the integral of eta over sigma is less than or equal to the integral of h naught over sigma, where this is the mean curvature in Euclidean space. Because the assumption is that you can put it in Euclidean space. Okay, so so this is sometimes or often stated as a statement about the Brown-York mass. But from this perspective, I just want to say that it's saying it's putting a given sigma and gamma, it's putting a restriction on what eta can be if you have any hope of filling it in. Okay, that you have to have an upper bound for the integral of eta. Now, this assumption in general, it's kind of artificial. Like, when can you isometrically embed something in Rn? But when n equals 3, it's pretty natural, because then it's just saying it has positive Gauss curvature. Or if it has positive Gauss curvature, then by the Weil embedding theorem, this can happen. But I just want to state things in sort of n dimensions. Okay.
So in other words, is that inequality violated in the contradiction of the mass theorem?
Yeah, exactly. Yeah, so this proof uses the positive mass theorem. And again, I guess what can I also say, but not write on the board, is so there's a conjecture by Gromov that without this kind of assumption, just take any sigma gamma Just then there's a conjecture that that there's some fixed constant such that the integral of eta is bounded by that constant that only depends on this data. Okay, so this could be viewed as verifying that. Well, the conjecture came later, I guess, but as verifying that conjecture in one very specific case. Well, not that specific. It's actually pretty broad. In 3 dimensions, it's very broad. Okay, so now let me just say, go back to the philosophy. So the philosophy is that, well, you should be able to get the same thing if you allow not just NNSC. I guess this was the whole point, so I should have emphasized it, right? That you get the same thing if you don't just allow compact NS and non-negative scalar curvature fill-ins, but also if you allow complete or. So this is with Lesord and Unger, and the theorem is that same theorem, but with complete or shielded fill-ins. That we get the same result. So it's literally the same proof. It's not anything. But the difference is that we then have to invoke versions of the PMT with this complete or shielded, but also with a corner. So actually, that's actually where the only technical work is here, is that we have to deal with the corner. So that's really maybe the only thing that fits the theme of this workshop, because that's the non-smooth part. But complete or shielded fill-in. Okay, so that's, yeah. So this was the part that I skipped, which is that or part is a complete fill-in. I don't require this. I could just do that. So that would be a complete fill-in. So it still satisfies all this stuff, but it's just not compact. Yeah, could be asymptotic. So in fact, one way of viewing this proof actually operates by building an extension in the outside. But actually, from this point of view, an extension from the outside is just a fill-in, a complete fill-in with where the sign on eta has been flipped.
So are you saying there's a restriction, for example, for the Bartnik or
Yes, for example. Yeah, but okay, that part's not interesting. So the extension, right? Well, it's okay. Well, yeah. So yeah, Bartnik extension, you'd expect typically the eta is positive, which means that when you view it as a fill-in, that's actually negative eta. So, but I just wanted to say that it connects a bit. But let me just write the last theorem, and then I can stop. So this theorem, which is based on a theorem of Meow, which I won't write down, but basically ours is a generalization of that. It says that, so this one, given this fully general thing, there exists a lambda such that any, so when I say complete or shielded, of course that includes compact, right? But I'll just say that explicitly, that I mean to, right? So that exists a lambda such that for any complete or shielded NNSC fill-in, well, you don't get the integral, but you at least get the minimum. So the minimum of eta is less than equal to lambda. Right. And so, yeah, Peng's version of this is just compact, but also there was some other stuff about assuming that, depending on the topology of the thing, but that's not important. I will say that this one uses the shielded Chodo-Schlee theorem that I put before, so it's not like we just proved that for no reason, that this was the application involved. Okay, so it doesn't use the PMT because it's not like a PMT type statement, but it uses that instead. Okay, I'll stop there.